Hello, everyone. My name is Harry. I'm one of the TA of the class PHYS4460 relativity, and I am responsible for the exercise class 2 and the problem set 2. All right, sure, let's start. Today I would introduce back what is a vector, what are one-form tensor, and also I want to give a brief concept about the coordinate transformation. So here, my exercise, this exercise class involves different short questions. You can see here, I want to make clear your concepts about the vector one-form tensors, and also introduce what is a coordinate transformation, what is exactly a so-called good coordinate systems and a good coordinate transformation. Okay, and also there are some practice here and 2 long questions for you to take up. If you have not finished your exercise class 2, please just turn off your video and just do it by yourself, and then watch this video to check your answer. So let me start now. So one can always find a set of basis vector. So maybe you just you have learned before in your first year of the university physics. So basically, a set of basis vector, you can just define basis vector if we are using a one-time coordinate and 3 coordinates for space and 1 for time, and there would be 4 coordinate system, and we can express with this. So basically, dual basis of one form, which is a exactly counterpart of the basis vectors. So for one form, U tilde alpha defined by E tilde alpha times a basis vector beta by delta alpha beta. Yep. I trust you guys have already learned Einstein notation before this class. So I just need to use the Einstein notation all the way. Express arbitrary vectors in terms of the basis vector. Maybe I should write smaller to let you guys to see. Express arbitrary vector. What do you mean arbitrary vector? So we would write down a vector form, just like you see a vector in high school study, and vector Vn would be equal to different component, maybe V1 times the basis vector, right, plus V2 plus blah 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 blah, and so on and so on. And so by Einstein summation, it would be this. Why? Because a basis vector, we use a subscript. Okay, subscript will describe a basis vector for to describe a vector, and the superscript. A superscript, see here, would be a one of the vector component, and so by this we can use it to express vector. How about express arbitrary one form? So arbitrary one form will if you use the first course about general relativity to be your textbook, so the notation of a one form is a P tilde, something like that, and it would be P tilde P alpha E to alpha. This because the dual basis of one form is superscript. You can see in up, and the component of one form will be down subscript. And therefore, we know that components of vector would be superscript, right? Superscript. Component of one form will be subscript. And component of vector basis is subscript, and one component of vector basis, which is dual basis, is superscript. All right. And let me introduce one more basic concept about what do you mean by bracket 10 tensor or 01 tensor 1121. So basically, it's just describe how many indexes in the superscript and also the subscript. So 10 tensor represent a component of a vector v mu. So there is a superscript index, right? Only one superscript index. So there's no any subscript index. So subscript here, superscript here. Yes, that's why a vector would be a 10 tensor. Okay. All the vector one form matrix and also anything can be a tensor, and P nu one form would be 01 tensor because this describes subscript, no superscript index, and one subscript index. All right. How about 11 tensor, which is a alpha beta? Okay. And you may wonder, there would be is any differences between beta alpha? Yes, there's some differences you may learn after you learn this chapter. Okay, and you have to care about the front, and the forward position of the index. So basically, you have to write gamma, something like that. Okay, you have to careful about the position of the indexes. So how about the Einstein tensor G subscript mu, which is a 2. Okay, G mu superscript to 0 tensor. All right. Okay, you may wonder, in the textbook, someone say what is a rank of a tensor or order of a tensor. So basically, you can just see figure 1. Okay, figure 1 is rank 0, data, rank 1 a vector, rank 2 matrix, and rank 3 just something like this. Okay. Okay. All right. After I introduce some basic concept, I would like to teach you about the coordinate transformations. So that's to see what is a general coordinate transform, is also called good coordinate transformation. That's to define a general coordinate system by xi and eta. Okay, we can write that eta is equal to in the function of xy, and xi is write down to be a function of xy, and you can see why the the expression will be just like this. Okay, how about we denote this these two equations to be 1? Okay, what do you mean by good coordinate system or good coordinate transformation? So basically, in order for this general coordinate to be a good coordinate transformation, we have to define two distinct points. Okay, x1 y1, okay, x2, y2. All right, and they would be assigned or represent different pairs of in terms of eta and c. And all right, and by the first two equations, and for instance, if the definition of eta is equal to x and c equal to x, eta equal to 1, and this case would not give a good coordinate. Why? Because the distinct point you can see x equal to 1, y equal to 2, and also you can see c equal to x, right? And we know that if you take x equal to 1 and another point have to x equal to 1, or maybe y equal to 3, these 2 points is same, but y components are not equal. They both have, after substitute in the first set of equation list, they both have c equal to 1 and eta equal to 1. All right. And mathematically, this requires that if delta c equal to delta equal 0, then the points must be same. So what do you mean good coordinate? If we choose delta c equal to delta eta equal to 0, then the point must be the same so that we can define a good coordinate. Otherwise, we would there would be appear such case if c equal to x, eta equal to 1. There's 2 points will have the same another general coordinate represented by c and eta, just like this case. Just like this case. So this is a bad coordinate. All right. If delta c equal to delta eta equal to 0, and the points must be same, or delta x equal to delta y equals 0. Easy. You just pop into this equation, both 0, delta x and delta y equals 0, or the 2 points must be the same. Oh, sorry. 2 points must be same. Okay, must be same. So it would not appear two different points with same set of eta and c and eta. All right, just like I highlighted case. So what do you mean by delta c equals delta eta equals 0? It appear a definition we have to know, which is Jacobian. Okay, here you can see the determinant bracket this guy, okay, would be non-zero. So basically these guys would be non-zero in order to define a good coordinate. So that if we choose a set of eta and c, it would not appear two different points. They must have a the one single point. Okay, this guy will be Jacobian. Okay, of the coordinate transformation. If Jacobian equals 0, the transformation at a point, a transformation is said to be singular there. Okay. All right, singular there. How about I introduce next page? So basically, you can see the next equation made in matrix form. Here, let you remind what do you mean by how to define vector. So how to define vector is say that it transforms under an arbitrary coordinate transformation and in the way that the displacement transforms as well. Okay, it follows the coordinate transformation and a vector follows a coordinate transformation and then the displacement transforms. All right, just like a vector. Let us define a vector. Okay, arrow can be represent. Okay, can represent delta arrow in by delta x and delta y. Okay, or even polar coordinate as you wish, and or in general delta eta and delta c, delta c and delta eta. You can see a vector can be represented by different coordinate system. And why I say so? Because this vector can be displaced by different coordinate. That in that mean which is by coordinate transformation. If the vector is given by x and y, okay. After coordinate transformation, we have to represent by a new coordinate system, represented by c and eta. We have to multiply a matrix that would displace that vector. Okay. Let's see. This is very clear. A small delta x and delta y. How the coordinate transformation change the components of the delta x and delta y and as a function of c and eta. You can see is this. Okay. You can see in this question by represented by a matrix that this matrix is completely the same as the first set of equation. Then we can define the matrix transformation as this guy. Okay. We just extract with this matrix in the first equation. Okay. We rewrite it in matrix form and we extract this matrix to be coordinate transformation matrix. Okay, sometimes eta would you see in some notes would be represented to be x alpha prime beta, yeah, something like that, which is the same a new coordinate system and the old coordinate system. All right, and you can see here, how about we write a arbitrary factor v. We just we should coordinate transform the component of the vector v, so a v alpha change to v alpha prime and equal to a coordinate transformation matrix times a V beta. Okay, and let's to see some practice. So basically, where these guys unprime. Okay, I should say a little bit more. Unprime index referred to xy. All right, and this guy referred to Cassia eta. All right, where indices can only take value 1 and 2, why we just choose 2 dimension because, and a vector can be defined as something whose component transform according to this equation. Okay, and this is a modern way which we now introduce. So let's do some practice. So I just looked at in some textbook, the coordinate matrix would be write down as this form. Okay. If you see this guy, aren't this guy not a how to say is this Lorentz transformation matrix? Okay, Lorentz transformation is just a coordinate transformation. Okay, you can see sometimes Lorentz transformation would use this guy as a symbol of Lorentz transformation. So it's one of the coordinate transformation, special coordinate transformation. So in our general relativity, we have to learn different kinds of coordinate transformation apart from the Lorentz transformation. So we all would use this big lambda of prime beta. Okay, and the inverse must be alpha beta prime. Yeah, and how about given a coordinate system x alpha and basis vector, yeah, and then we can define as sometimes in some notes we can someone will define the E the basis vector equal to this guy. So be careful to and then so now here is practice. Now change coordinate system from x mu to x prime mu. Okay. Oh, so transformation of a vector. Okay. In some textbook, how about we just change this vector, okay, which is the basis vector, okay, would be a mu, okay, and this guy must times a coordinate transformation, right? Okay, let's say rho mu. You just choose anything you want the index to be, and here would be the E rho. Okay, prime. Okay, sometimes you may see mu this in some textbook. Okay, and then we know that the original basis vector would not change by a coordinate transformation. What we have to change is the components of the vector itself, and a vector would be vector times this, which is okay times this, which is okay. Let's see. And how about the transformation of one form? Okay, we just apply a inverse coordinate transformation matrix. So you can see here this guy, if you may be very confused, actually this guy is just this dual basis, okay, dual basis, and you can see the after coordinate transformation, it will have a this guy. So this time we use the inverse coordinate transformation matrix and times the dual basis. Okay. Prime. Yeah. And then it equal to rho dx rho prime. Therefore, hence we know that a one-form component transformed by this. All right. Equal to someone maybe ask why the coordinate transformation matrix can be written as this form. Okay, you can see all the coordinate transformation is described by the derivatives, first derivative of a new coordinate system over the old coordinate system. If you write this guy as alpha beta in Einstein notation, it is very legal to do that. Okay, and transformation of one tensor. Okay, we have to apply one transformation matrix and one transformation inverse matrix with different indexes. So the answer is just very clear. Okay, alpha prime mu a index 1 by 1 to transform. Okay, you can see what do you mean by 1 by 1? Okay, alpha beta. Okay, alpha, how to transform this alpha to R prime, and to use alpha times a coordinate transformation matrix to be alpha prime. All right, and the subscript, the beta, okay, I use mu, and there's a inverse coordinate transformation matrix would be mu, and the subscript beta prime. All right, and would be a coordinate transformation. So therefore, a transformation of 2-1 tensor would be just like T mu nu alpha. Okay. I should change the different position. Okay. Okay, easy. Oh, after that, I think you guys have some basic knowledge about the coordinate transformation and what is a one-form tensor and vector. So how about we do the non-questions? If you didn't finish that, if you didn't try it before by your hand, you should not look at the answer. Okay, should not look at the answer. Okay. B. The first question is find the transformation matrix L I prime J. Okay, sometimes in the question would not use big lambda, and also the inverse transformation matrix correspond to the rotation of the coordinate axis. So basically, a rotation of coordinate would be to be a new coordinate system, right? Which is a coordinate transformation, and through an angle theta about the z axis. Okay, x3 axis as shown in the figure 2. So basically, here is a set x3 axis is rotate to anti-clockwise. Okay, and by theta, and you can see in this figure, I want to teach you how to decompose the different coordinate system in terms of x prime, and x prime would be the function of the x unprimed system. First Q answer, all right. First Q answer. And how about we use to see the figure, the component X with respect to new prime basis. Okay, the new prime is X. Let us to try one by one. So we write down X prime 1, X prime 2, X prime 3. Okay, we know that X prime 3 must equal to X prime X3, right? There's no any transformation to deal with the X3, yeah, because it's allied to each other, and we cannot decompose into different new coordinate system. And how about the new coordinate system decomposed by the old coordinate system X unprime? So basically, you can see X1, okay, this X1, okay, is equal to X1 cosine theta plus X2 sine theta. It's very trivial, right? You just decompose a vector, you represent it by this vector, right? Easy. And you can see a X2, in X2 the component is a X2 times sine theta, right? And here you can see here is a X1 times cosine theta, and we can decompose one of the X1 prime, and X2 prime is just to be the same. You just decompose this basis vector, basis coordinate into X1 and X2. We'll use after calculation, we'll obtain this. Easy. So after the decomposition of by a unprimed system, you will appear a form to see just like this, right? Right. Why we can express it into a matrix form, you will know that. And of course, we can inverse it to see whether the inverse coordinate transformation would be the partial x beta unprime over a prime system of partial x. Okay, how? We just write down x1, x2, x3. Okay, here x3 is equal to x3 prime. Okay, now we want the inverse coordinate transformation matrix derived from we use unprimed system to represent to be represented by a prime system, the new coordinate system. So how about we just to see which we use x1, okay, and represented by these two coordinates. Okay, simple mathematics. And this vector, how this vector will be represented by the x1 prime, x2 prime. It's very easy. After calculation, up here then. Okay, easy, right? Because this is the x1, x2 prime. Okay, how about this direction? Okay, you can just project the x1, this vector, into the prime coordinate system to see. And another thing is that the x2, how the x2 represent. Okay, let's say I just write down a trivial x2, and we know that we can project to x2 prime, and also x1 prime. Okay, and then you will find x2 is equal to x1 prime sine theta plus x2 prime sine cosine theta. Easy, just by simple mathematics. Okay, theta here, x2 must be times cosine theta, right? And here, this component will be x1 times sine theta. Easy. Maybe I write a little bit messy, and you can basically write to try this simple mathematics by your own. And then we know that we can obtain such coordinate transformation matrix, right? And the x1 prime, x2 prime, x3 prime, write down the coordinate transformation matrix is 0, 0, 1, 0, 0, cosine theta, sine theta, minus sine theta, cosine theta. Okay, I just write down all the way this component, okay, to be a matrix and times a prime system. All right, you can see the L I prime J is equal to this guy. Okay, I should. Now I'm very lazy, and I prime J out there. All right. You can do as the same way. You can find the inverse coordinate transformation matrix. All right, easy. How about the question 2 answer? The question is, who is going to ask if a VI, okay, are the component of rank 1 tensor, okay, which is have to be a one-form components, right? And so that the del dot V, okay, is equal to this guy is a zero rank tensor. Basically, zero rank tensor is zero order tensor, which is a scalar. Okay, and how do we do that? After we rotate the coordinate system by this, okay, it's given by okay, it's given by V times stop prime. Okay, V prime stop prime. Why we do a rotated coordinate system? Okay, because we want to show which is invariant under a coordinate transformation. What do you mean? It's scalar. Okay, a temperature, let's say, okay, no matter we do any coordinate transformation, will be invariant, will be the same under the coordinate transformation. Okay, any coordinate transformation. Why is the case? I'll show you. Let's see. Here is the represented del dot V. All right, it's equal to this form. And after a prime system, we would know that prime V prime, and which is just basically the inverse coordinate system by J I prime times times A J times LIK VK. Yeah, we can write it in this form, which is the completely xj xi prime I. Okay, we just do some massage with this because we can write the form as is okay, VK. This is the I, this is the K. Yeah. Here we can see the two coordinate transformation. I, J prime, and this guy would be I, and here is K prime times the K over XJ. Yeah. And there is use the orthogonality relation. Okay, what is a orthogonality relation? If two coordinate are inverse, like okay, IK prime, and this is IK K prime J, okay, will be delta IJ. Okay, the inverse and the not inverse coordinate matrix will have such property. Okay. And we can use this property to do this question. And we revise this guy. Is equal to delta. Okay, I should solve. Okay, delta JK VK delta XJ, which is completely okay. This sorry, I made a mistake. Delta delta sorry, delta K prime J. Sorry, I made a mistake here. K prime J I prime. Okay. And finally, we know that after this J and K, this four index contracted, it will have VK over XJ. And this was so the primary system of the divergency of the V is after the rotated coordinate transformation, it would be the same as before and scalar. So this is a rank 0 rank tensor. All right. Here is that's all what I want to teach you guys. And this is very trivial. If you make sure you know how to massage the coordinate transformation of a unprimed it to a primed it, and also unprimed it to an unprimed it. And sometimes, for example, the Q2, you have to use some this delta ij property of the transformation matrix to deal with some tricky mathematics trick to show this A scalar is invariant anticoordinate transformation. You would be, yeah, you have to very get used to it. So that's all of my exercise task. Thank you very much.